So we completed the hybridization involving s and p orbitals. Now let us see the hybridization involving d orbitals. Hybridization involving d orbitals. We know that in the first period of the periodic table we have 1s orbital getting filled. Second period we have 2s and 2p orbital getting filled. In the third period we have 3s, 3p and 3d orbitals, but only 3s and 3p orbitals are getting filled. So in third period we have 3s, 3p and 3d orbitals, and I told the 3d orbitals are vacant in third period. And in fourth period we have 3d orbital getting filled, 4s and 4p orbital also getting filled. So in fourth period we have 3d, 4s and 4p orbital getting filled. So hybridization involving 3s, 3p and 3d orbitals are possible. Also hybridization involving 3d, 4s and 4p orbitals are possible. So these both are possible, whereas suppose we have 3p, 3d and 4s. This hybridization is not possible because there is a large difference in energy between 3p and 4s orbital, whereas 3p, 3d, 3s, 3p, 3d they have almost same energy, and 3d, 4s, 4p also they have same energy. So we can have hybridization. Which all orbitals can be involved in hybridization? 3s, 3p, 3d, all 3d, 4s, 4p orbitals. So let's study two examples in which hybridization involves d orbitals. Okay, so the two examples are, and we have two types of hybridization possible in which d orbital is involved. The first type is SP3D hybridization, and second type of hybridization is SP3D hybridization. You have only two types of hybridization involving d orbitals to study in class 11. We have more types of d orbital hybridization which you will learn in class 12. So 11th you are going to study about SP3D hybridization and SP3D hybridization. Okay, and this d orbital hybridization is found in period number 3, 4, 5 elements. Now we are going to study an example, one example for each type of hybridization. The first example is for SP3D hybridization, that is hybridization. The first is SP3D hybridization. And example for this is formation of PCl5 molecule, that is phosphorus pentachloride, and we know phosphorus is in third period of the periodic table. Okay, so let's see how this PCl5 undergoes SP3D hybridization. In PCl5 the central atom is phosphorus and the atomic number of phosphorus is 15, and phosphorus is in third period. So it takes the noble gas configuration of the second period, which is neon. So when we write the electronic configuration, we can write the configuration as neon 3s2 3p3. This is the electronic configuration of phosphorus. And you know phosphorus is in group number 15, so it has 5 valence electrons, 3s2 3p3. Now let's draw the orbital diagram. The orbital diagram is 3s, 3p, and we have 3d orbitals also, but it is vacant. So 3s2 3p3. Okay, now what will happen? We have only 3 half filled p orbitals, 3p orbitals, and we know the hybridization is SP3D. But you can see in the ground state of phosphorus, the d orbital is vacant. So what will happen? Phosphorus will get excited, and in the excited state, one of the electrons from 3s orbital will be promoted to vacant 3d orbital, and it results in SP3D hybridization. So next I am going to draw the orbital diagram for phosphorus in excited state. The orbital diagram will be 3s, 3p, 3d. So we have SP3D hybrid orbitals. There is one s orbital, 3 p orbitals, and 1 d orbital will hybridize to form how many hybrid orbitals? 1 plus 3 plus 1. 5 new hybrid orbitals of same energy and shape. Okay, now what will happen? It results, how will it form PCl5? We know that chlorine atom, electronic configuration of chlorine is neon 3s2 3p5, 3s2 1 2 3 4 5, and you can see there is a half filled orbital in chlorine. So what will happen? The 5 half filled or 5 hybrid orbitals, SP3D hybrid orbitals on phosphorus will overlap with half filled 3p orbital of 5 chlorine atoms to form 5 PCl sigma bonds. Okay, so we can say the hybridization in PCl5 is SP3D, and shape is trigonal bipyramidal with 2 bond angles. The bond angles are 120 degree and 90 degree. Now already we discussed the shape of PCl5 molecule on the base of ESEPR theory, and we saw that the shape is trigonal bipyramidal with 2 bond angles 120 degree and 90 degree. So if you are asked to explain the formation of PCl5 molecule on the basis of valence bond theory or on the basis of hybridization, you have to explain like this. Okay, now I am going to draw the shape of PCl5 molecule. The shape is trigonal bipyramidal PCl5. And you know there are 2 types of bonds in PCl5, 3 PCl bonds which lie in same plane are called equatorial bonds, and these equatorial bonds make an angle of 120 degree, and we can see these are the equatorial bonds. This is an equatorial bond, this is an equatorial bond, sorry, this and this, these are the equatorial bonds. Okay, now we have 2 axial bonds. Which are the 2 axial bonds? This is an axial bond and this is also an axial bond. Okay, so we have 3 PCl bond lying in same plane and 2 PCl bonds which are called axial bonds, which makes an angle of 90 degree. So this is the shape trigonal bipyramidal with bond angle 120 degree and 90 degree of PCl5 molecule, and in PCl5 the phosphorus atom undergo SP3D hybridization. Now here comes a question. The question is, the axial bonds are longer and weaker than equatorial bonds, or why PCl5 molecule is very reactive? So the answer for both the questions are same. What is the question? The axial bonds are longer and weaker than equatorial bonds, or why PCl5 is very reactive. Now the answer for both the questions are, we can say that the axial bone pair, they suffer more repulsion from equatorial bone pairs. So, the axial bones are longer and weaker. And since these axial bones suffer more repulsion, what will happen? They are unstable and very reactive. So, PCl5 molecule is very reactive because of that longer and weaker axial bones. And why these axial bones are longer and weaker? Due to more repulsion from equatorial bones. Okay, so this is the shape of PCl5 molecule on the basis of hybridization. Now we have one more type of hybridization involving d orbitals, that is SP3D hybridization. So the second type is SP3D hybridization. Now you can see S1P3D2 means total 1 plus 3 plus 2, 6 hybrid orbitals are formed. Now let us discuss SP3D2 hybridization taking formation of or shape of SF6 molecule, sulfur hexafluoride. Okay, now how will you explain the shape of SF6 molecule? The central atom is sulfur. So, sulfur, central atom, its atomic number is 16 and electronic configuration. Now, this sulfur comes under oxygen, means it is in group 16, and we know how many valence electrons for oxygen there are. 6 valence electrons. So, sulfur also has 6 valence electrons. So, neon 3s2 3p4. Now, when you draw the orbital diagram, this is 3s 3p and we have 3d orbital which is vacant. So, 3s2 3p4. Now, we know that the hybridization is sp3d2. So, what will happen for hybridization? The sulfur atom will get excited. And what happens during excitation? We know there are 2 electrons in 3s and in one of the 3p orbital there are 2 electrons. They will get unpaired and 3s 1 electron jumps to one 3d orbital and from 3p also it jumps to another 3d orbital. So, I am going to write the electronic configuration of sulfur in excited state, or the diagram is 3s 3p, this is 3s 3p 3d. Now you can see we have 6 half-filled orbitals, 1s 3p and 2 3d orbitals. So they will undergo sp3d hybridization, sp3d2 hybridization, and we get 6 hybrid orbitals of same shape and energy. Now this is the formation of SF6. So let's try the electronic configuration of fluorine atom. Fluorine atomic number 9, 1s2, 2s2, 2p5, 1s2, 2s2, 2p5, 1, 2, 3, 4, 5. And you can see there is one half-filled orbital in fluorine. So it is SF6. So sulfur has 6 hybrid orbitals. These hybrid orbitals will overlap with half-filled 2p orbital of 6 fluorine atoms to form 6 SF sigma bond. And the shape of SF6, as we have already discussed in BSc-PR theory, is octahedral with bond angle 90 degree, not 180, 90 degree. So when you draw the shape of SF6 molecule, how can you draw the shape of SF6 molecule? Sulfur, fluorine, fluorine, and this. So shape is octahedral with bond angle 90 degree. So this is sp3d2 hybridization. Okay, and example for this is SF6 molecule. So with this we completed that hybridization involving d orbitals, the two types, that is sp3d and sp3d2. Now next let us see how to find the hybridization of a central atom in a given molecule. So suppose a molecule is given, and if you are asked to find the hybridization of the central atom, we have a formula. So next is to find hybridization of central atom. Now I told there is a formula, and the formula is X is equal to half into V plus M minus C plus A, where X is the number of hybrid orbital. Means if X is equal to 2, then the hybridization is SP. Then X equal to 3, hybridization is SP2. X equal to 4, hybridization is SP3. X is equal to 5, hybridization is SP3D. Then X is equal to 6, hybridization is SP3D2. Okay, now X is equal to 2 means we have 2 hybrid orbitals, S and P. 3 means 3 hybrid orbitals, SP2. Okay. Now what is V, M, C and A? Now capital V represents the number of valence electrons in central atom. Now capital M represents the number of surrounding monovalent atoms, the surrounding atoms. Now what is C and A? C is charge of cation and A is charge of anion. Okay, so let's apply this formula to find the hybridization. Few examples we will do. So example 1, BeCl2, and the formula is X is equal to half into V plus M minus C plus A. Now half into V, valence electrons in beryllium is 2. Then number of monovalent atoms attached to it is 2 chlorine atoms, so again plus 2. Then any charge given? No, it's not a charge species, so plus 0, minus 0 plus 0. So answer is 2. X is equal to 2 means which hybridization? SP hybridization is involved. Now next example is example 2, carbon dioxide. Now X is equal to half into number of valence electrons in carbon is 4 plus then carbon dioxide. Here we have no monovalent atoms, so we have 0 minus 0 plus 0. Okay. Now the hybridization is 4 by 2, which is equal to 2, which means it is SP hybridization. Okay. Now next we have number 3. 3 is NH4 plus. X is equal to half into number of valence electron in nitrogen is 5 plus 4. Then it's a cation with plus charge, so it is minus 1 plus 0, which is equal to 4. So X is equal to 4 means the hybridization is SP3 hybridization. Now next example is XCF4, xenon tetrafluoride. X is equal to half into 8 plus 4 fluorine atoms, so 4 minus 0 plus 0, so 6, which means the hybridization is SP3D2. Now next example, let's see for XCF2. X is equal to half into 8 plus 2 minus 0 plus 0, which is equal to 5. So the hybridization is SP3D. Now the last one is PCl5. X is equal to half into 5 plus 5 minus 0 plus 0, which is equal to 5. So the hybridization is SP3D. Okay, so this is how we find the hybridization of central atom in a molecule. So with this we complete the valence bond theory based on hybridization. Thank you.